Hello, and welcome to Physics for Play. In today's episode, we're going to be looking at how to compute the wave energy for standing waves on a string. Let's get started. So we are going to be using as our source today AP French's Vibrations and Waves. We are going to be doing problem 611 from that book, showing you how to compute the energy in the standing mode on a string. So if we take a quick look at that problem, we can see that it says that it wants you to find the total energy of vibration for a string of length L that is fixed at both ends, oscillating in its nth characteristic mode with an amplitude A. The string has a tension T, and it has a total mass M. And it gives us the hint that it wants us to consider integrating the kinetic energy at the instant when the string is straight so that it has no potential energy. It also has a part B, which wants us to compute the total energy of vibration for the same string vibrating in a superposition of normal modes. And we'll get to that in just a little bit. But let's go ahead and start by defining some constants. And I've taken the liberty of defining those constants beforehand, so I'm going to just pop those in here. So the constants we are going to define are the wave speed, given by v wave here, which is equal to the square root of the tension in the string divided by the mass per unit length mu, which you can get by just taking the total mass divided by the length of the string. We also have the wavelength. So for a string that is fixed at two ends, the maximum wavelength would be 2L, 2 times the length of the string, because you only get half of the wave in the first mode. And we can derive from that that the wavelength, lambda n, is going to be equal to 2L divided by the mode number n. For the wave frequency, we can define that as Fn, which is equal to the wave speed divided by the wavelength. The angular frequency, omega sub n, or omega n, is 2 pi times that frequency. And the period, which is the time it takes to complete a full cycle of oscillation, is 1 over the frequency. Now we're going to go ahead and just define these beforehand so that we can use them throughout the video. The next thing I want to do in order to compute the total energy is I am going to define the shape of the normal mode of the string, the nth normal mode of the string. And I can do that easily enough. There are equations for this in both the source material, vibrations and waves, and pretty much any material, any reading material you have on waves and vibrations, you can usually find an equation for the waves on a string, standing waves on a string fixed at two ends, and that'll just be given by sine n pi x over L. And I'm going to put a sine omega n times t. Now you might see slightly different forms for this. I am choosing a sine rather than a cosine here because I want to use my hint here. I want to use that the kinetic energy is going to be, I'm going to use a time where it's all kinetic energy and no potential energy, which you can see here by plugging in t equals 0 will give you all kinetic energy, no potential energy. You can see it's no potential energy because t equals 0 will make this sine 0. The whole thing will be 0. So there's no stretch. There's no stored potential energy at t equals 0. So that'll make life a little bit easy. Now we want to go ahead and plot this just to show that it is what I say it is. It looks like a standing wave. Get a nice visual here. We'll plot from 0 to 1. And you can see I'm not going to get anything if I try to plot that because I have undefined variables here. So let me go ahead and define all of these. We'll set the amplitude equal to 0.1. We'll make the mode number 1. We'll make the length of the string 1. And I also have some constants up here I need to define. So I'll need to define the tension and the mass per unit length. So I'll say the tension. I don't want it to vibrate too fast, so I'll give it a smaller tension. And I will give it a mass per unit length, which you can get that mu character by escape and escape. And we'll do that. And we should be getting a plot here. Why aren't we getting a plot here? Oh, because I have not defined the time yet. So let me plug. You can see I've got just a flat line. If I plug in something a little bit bigger than t equals 0, you can see I start to get some kind of amplitude there. If I can jump up to the second mode, you can see I get more peaks in my wave. And same thing if I jump up to the third or higher modes. We can get an even better visualization of this by going ahead and animating this. We'll animate it for 10 seconds and let's see how that looks. Note, I do have to get rid of my time here since my time is now defined as part of the animation. So I can go ahead and do that. And we should see, probably want to do a lower mode number because that's going to oscillate way too quickly. And I need to put a plot range in here because it's going to resize the range and it's not going to look super nice. So we'll plot that for a range that's just the amplitude. We'll go from minus 0.1 to 0.1 since I've chosen an amplitude of 0.1. So you can see that oscillates nicely. I can go to higher mode numbers and you can see it oscillates even faster. So I'm going to go ahead and pause that. We've got the shape of our nth normal mode. And the next thing I want to do is I want to use that function to compute the total energy of the wave. So what I'm going to do, I'll throw in another bullet here. We have the total kinetic energy per unit length is given by 1/2 the mass per unit length times the velocity of that point on the string. So what we're imagining here is we are breaking the string up into infinitesimal elements. So let's say I'm looking at some small piece of the string right here. If I look at a small length of the string and I would just get the mass, I would get the kinetic energy of that point by taking the mass per unit length times the length of that infinitesimal element times the velocity of that element squared. So the kinetic energy per unit length is given by that. The total energy is going to be determined by integrating over the length of the string. So let's go ahead and do that now. First thing I want to do is I want to define the velocity of a point on the string. So I'm going to say v of x and t is equal to, v of x and t is equal to, let's actually pull out an input palette here to make life a little bit easier. It's going to be equal to the time derivative, so I'm going to take a derivative with respect to t, of this y of x and t that I've already defined. So I'm going to go ahead and do that. We've now defined our velocity. We can actually see what it looks like, just as a sanity check. You can see that compared to my original function, we still have an a sine n pi x over L. We've got an a sine n pi x over L. But now I have a cosine that shows up because we've taken the time derivative. When I take the time derivative of this sine, we get a cosine function. So everything looks good here. So next, what I want to do is I want to integrate this function right here. Can I copy it from the text portion? Let's see, am I going to get lucky? Nope, it's not going to let me do that. I'll try it and see. Oh, that worked, yay. Life just got a little bit easier. So I'm just going to copy and paste that so you can see our kinetic energy is 1/2 or excuse me, our kinetic energy per unit length is 1/2 the mass per unit length times the velocity at the portion of the string that I'm looking at. And we're going to integrate over that. So I'm going to go ahead and, wrong thing, didn't want to do that. Let's get rid of that, don't need this. Let us put that in an integral. And we're integrating over x. And we're going to go from x is 0 all the way across the length of the string. So we're adding up all of the different kinetic energies at each little tiny bit of mass, mu dx along the string. So we'll go ahead and do that, integrate, and you will see I am, let me get rid of these guys. I think that's maybe giving an issue. No? I think there is an issue. Let me just retype this. I think I can't technically just copy from. Okay, that's good. Okay, so we'll. Yeah, I think it is going to give me an error because I'm copying it from text that's not code. So we'll just do this the usual way, the old-fashioned way of actually typing things in by hand. If I do that, there. Now I've got my answer. Now you can see here that it's a little more complicated than it needs to be. For example, if I look here, I've got a sine 2n pi, but that's got to be 0 because n has got to be an integer. It's the mode number. And sine of any integer times 2 pi is always going to be 0. So let's tell it to make some assumptions here. So we'll tell it assuming, if I can type, assuming, we will have it assume, I'm going to have it assume two things. So I'll give it a list of things to assume. Thing number 1 is I'm going to have it assume that n is an integer. And I am also going to have it assume that time is equal to 0. Why am I having it assume that time is equal to 0? If we look at time at t equals 0, we can see that our string is not at all stretched. So much like the problem said in our original hint here, we're going to integrate the kinetic energy at the instant where the string is straight. So let's go ahead and do that when the string is straight, which happens at time t equals 0. We'll do that. And you can see we've got a nice simple form for the total energy. That total energy is given by the amplitude squared, which is generally going to be true. That'll be true not just for waves on a string. It'll be true for electromagnetic waves. It'll be true for sound waves. You're always going to see that amplitude squared here. We also have the mode number squared here. And then we also have some properties of the string. So for example, a string under more tension will have a larger energy of vibration. So we've done part A, and that's worked out quite nicely for us. I'm just going to minimize that. Now we're going to move on to part B. So part B says, calculate the total energy of vibration of the same string if it's vibrating in a superposition of normal modes. Now, this is a little difficult to read because the photocopy of this version of the text didn't come out great. So I'm going to write it out here. And in fact, I'm going to actually start with this. I'm going to start with this to, since there's going to be a lot of repetition here, but we're going to plug in the first normal mode. So we can see we've got an A1 sine pi x over L. The division line didn't show up there, but it should be, we know it has to be there because the units don't work out if it's not. So it's A1 sine n pi x over L. They actually use a cosine here, so I'll change that to a cosine. And it's the frequency of the first normal mode. And to that, we're going to add what appears to be the third normal mode. So we've got A3. I'll just copy that, change that to a 3. Now it's the third normal mode, so it's 3 pi x over L instead of 1 pi x over L. It's going to have cosine omega 3 t. And one more thing here, you can see this is phase shifted by pi over 4. So I'm going to just add plus pi over 4. That look a little nicer. So we've got a new function of y. Now you might think, hey, let's just do the same trick we just did. Take the kinetic energy when the string is completely straight, so that it has no stretch in it whatsoever. And then the kinetic energy will be the total energy since it's not stretched and it doesn't have any potential energy. I can't do that very easily here because of this phase shift. It would take some effort, assuming that there is some time when the string is completely stretched out so that there's no stored potential energy. It's going to be difficult to find since this doesn't even overlap. So we've got to try a new trick here. Fortunately, we already know what the energy per mode is. We just solved that in part A. And here I just have two modes that are excited. And I can just copy straight from part A what the answer is. I can put two normal modes, the first one being the first mode, so it'll have an amplitude of A1 and a mode number 1. And then this third mode is also excited, so that'll have an amplitude A3 and a mode number of 3. The tension is the same, the length of the string is the same. I just evaluate that, and I get my answer. If we want to simplify this, of course we can. We can factor a few things out, make it a slightly nicer form. But you can see we've got a pretty nice form here for the answer, even though it's a superposition and it's a little more complicated than the answer we got in part A. Now, it's always helpful to just check things and make sure things are working the way you expect them to. So we're going to do a double check on the energy, just to make sure we computed it correctly in part A. Because we only did it for the kinetic energy. We computed the kinetic energy per unit length. We integrated it over the length of the string to get the total energy. Well, we could do the same thing for the potential energy just as a check. So let's just do the same thing for the potential energy. We're going to show that the total energy is the same when the total potential energy is at a maximum. So we're going to show that it's the same as the answer we got in part A. So to do that, we're going to take the potential energy per unit length, which is given by 1/2 the tension times dy dx squared. So we're taking the derivative of the wave function with respect to x, whereas before we had the velocity, we were taking the derivative of the wave function with respect to time. The total energy is going to be determined by integrating this potential energy per unit length over the length of the string. So we're going to do that here. And since I've already done it above, I am just going to copy this whole thing, and I'll put that down here. Now I'm not doing the velocity. Instead, I'm doing dy dx, which I get not by taking the derivative with respect to time, but by taking the derivative with respect to x. So I've now defined dy dx. And I don't have velocity here. I have dy dx, which I'm just going to plug in. And I don't have mass per unit length. I have the tension here. So I'm just copying the potential energy per unit length equation. I think this is everything I need, so we're just going to go ahead and evaluate. Let that run for a second. And oops, I did a naughty thing because I defined y of x and t here, and I never undefined it, so I should go back and define this whole thing not as the superposition, but just as the normal wave function, generic wave function that we defined in terms of a mode number n. So we'll rewrite that. We'll try this one more time. And we get 0. Why are we getting 0? Well, we need to do this when the total potential energy is at a maximum. And as we saw, the total potential energy is at a minimum at time 0. So I'm at time equals 0 now. There's no stretch in the spring. It's all kinetic energy, and you can see it's about to pop out right here. Here it's starting to get a lot of potential energy because it's stretched. And this happens a quarter of the way through the period of oscillation. So I cannot, if I plug in time equals 0, here's time equals 0, there's no potential energy here. So of course I'm going to get 0. So I can't plug in time equals 0. I need to plug in the a time when the potential energy is at a maximum, which occurs a quarter of the way through the period. So that will be the period divided by 4. And if I run this, you can see I get the same answer that I got for part A. Namely, I've got an amplitude squared n squared over pi squared, amplitude squared n squared pi squared t. Again, amplitude squared n squared pi squared t over 4L over 4L. So that's just a nice simple way to check. You can see if I go a little before that period, same functional form, but it's just not quite as much potential energy. Some of that energy is going into the kinetic energy. So that is a nice, easy way to compute the energy stored in a wave. We will stop here for this time. Go ahead and like the video if you liked it. And if you'd like to see more of these, please click subscribe.